Hello, everybody. This is 5.1. We'll start this chapter with exponential functions and and their graphs. So, if you look at exponential functions, by definition, you have f of x equal b um, to the x. So x is the exponent, not to mix or confuse with something like x, let's say x squared. This is not exponential function, right? This is a square function. This is a square function. So exponential function is where you have a base, and for example, x or the variable is the exponent. In this case, the base has to be positive and it cannot be one. Um, all right. So it is an exponential function, and the domain is the set of our numbers, and we're going to see that in a few seconds. So let's take an example, and you see it's f of x as 2 power x. The domain is negative infinity to infinity because you can use anything, any number for x, right? However, here the base is 2. It is positive, and 2 of course is not 1, so that's the condition in the base. And of course you could have let's say g of x equal negative 2x. That's not, the base is negative. This is a negative 1. This is a negative 1 times 2x, so the base is still positive. So if you want to graph, of course, this, you can use the normal substitution for x and find the points. And you need to get used now to the rules of exponents. So if you have, for example, f of 0 is 2 power 0, which is a 1. If you have a negative exponent, that makes the base reciprocal. So these are some of the things to review. So you may need to review exponents, right? And these are the laws of exponents that you need to review and strengthen. Make sure you know how to use. So if you have for the multiplication, same base, you add. Division, same base, you subtract. X minus y, not y minus x. Two exponents, we multiply. The multiplication, so versus uh, a plus b power x, for example, that does not equal something like this, right? So in the multiplication, you can separate them. In the division, you can also separate them, right? But you cannot do that for addition or subtraction. Some examples as a review. So these examples are going to be enough to do the lecture activity and the homework. So for example, 16 to 7/4, and so 16 to negative 1/2. This is a multiplication. So you're going to add, so 7/4 plus negative 1/2. You add exponents because it's the same base. And then you find what it is and you do the evaluation there. You have this division with this exponent. So since we have division, that means we're going to need to subtract the exponents, find out what that is, and simplify. So this is pretty much like a review to algebra and intermediate algebra, for this 5.1. So if you have two exponents, so maybe we should do parentheses on this. So you see that's an exponent to another exponent. You're going to multiply the exponents and simplify. A negative exponent means the base and becomes positive. Use the reciprocal, so it's 64/1. right? And negative 2/3. So it's like 64 over 1, negative 2/3. You can think about it this way if you want to, or you can just think about it this way. Either way, for this to be positive, this 64 has to come down. If you do it this way, then the fraction needs to switch to a reciprocal, and this becomes positive. So whichever way you do it, you should end up with this answer. And you can do this on a calculator, or you can use to simplify the reverse. We know 1/3 times 2 is 1/3 times 2 over 1 is 2/3. So 2/3 is this and that. So you can use that to separate them, and that will take care of it. Cube root of 64 is 4, and 4 squared is 16. When it comes to for this other example, that's low 4, and you see the 16 and the 81 are not same, so we're not going to add exponents, but we can figure out each one by itself. So we figure out each one by itself when we do the operation. Same thing for these low 5, 3 and 2. They're not same base. So you're not going to subtract the 1/2 and 1/3. So you take care of each one by itself. But if it was like 3, 5, and 3 square, that's 5 minus 2, right? 27. So that's what you need to identify when you review these. How do you apply the rules and how the rules apply? So if we want to sketch these 2 power x function, we're going to use some points like here. Let's take the 0. So we have the domain negative infinity to infinity. So we can try 1, 2, 3, 4, 5, negative 1, negative 2. So for the values here, it's 2 power 0, that'll give you 1, 2 power 2, that'll give you 4, 2 power negative 1, they'll give you 1/2, and so forth, right? So then you get the points. So this one will give you now a 0, 1 point. This one, the x is 1 and the 2 point. This one will give you, right? So you get these points. And when you put these points on the graph, you're going to see 0, 1, 1, 2, negative 1, 1/2, and you'll see. So you'll see that these graphs form, and as far as you take the graph is going to keep going toward this x-axis here, and it's going to grow exponentially this way. So you can notice something, that the graph, it doesn't matter how you decrease this number, it's 1 over 32, 1 over 16, it's not going to become 0. So it happens that this is going to become a horizontal asymptote here. So let's see some properties based on what we saw. If we have this exponential function, the domain, as you see, is negative infinity to infinity. You can try any number and it works. However, see the range. The range is only this side. There is no function below the x-axis, so the range is going to be positive. The range is 0 to infinity. It does not reach 0. This is 0. It does not reach it because that's a horizontal asymptote there. But the limit towards negative infinity will be 0. The graph passes through the point 0, 1. It is continuous function over its domain. It is an increasing function, and this is a growth, so it is an increasing function. One thing, so it's important to know this, and if some transformation happens to this graph, then you're going to adjust based on that. The base E is, this is just so everybody knows where this come from. You don't have to memorize this formula, but you need to know what this irrational number is. If you do it on your calculator, you'll get a number like this, 2.71, so forth, doesn't end. And this came from this limit, and I leave for you in the notes here these steps. So you can try and practice and see as you increase the exponent m, the number, it goes towards the irrational value e. If you were to graph this e, remember e being a 2.71, so e being a 2.71 x, that's a base that is of course positive. It's not 1, but it's also greater than 1. Just like we saw in this example, this growth, this increase, it happens because this base is also greater than 1. So it's expected that's going to happen for this e power x. You can use the same technique in the past to use points. So you can, let's say now you can do it this way. You can say 0, 1, 2, as many points you want, -1, -2, and you substitute and you do on a calculator, e power 0, e power 1, e power 2, e power -1, e power -2, and you put these points. Shape-wise, it's going to look just like the other two x. Of course, it's going to be a little bit different based on the substitution. And these are, of course, the points talked about. Can approximate these points to graph. And if you sketch it, of course, it's going to look that way. So in this section, that's what we're looking so far at. And some of the techniques that extra that you also need to know when it comes to, let's say, solving equations, and they are exponential equations. But other questions, let's say from the homework and lecture activity, they're more of review of exponents and what we did so far in this review of algebra for exponential functions. So let's say you're asked to solve an equation for x. There are some cases we're going to look at. This is one case where we use this technique that if you have, let's say, a power b equal a power c. Example, 2 power b equals 2 power c. You see, if these bases here are the same, there is no way this is going to be equal unless b is equal to c. So let's even change b. Let's call it 5. So if you look at this picture, when would this numbers or sides are equal? It's not possible for this to be equal unless c is equal to 5. So we can use this technique here, and if these bases are not the same, you're going to try to see if they are the same. So this is possible only if b is equal to c, right? And so this is 6. This power. Maybe not cover the writing. Maybe do just like something like this. And this is another exponent. These cannot equal. These are possible if and only if 3x minus 4 equal 5, right? Because the 6 is equal to 6. All right, so add a 4 divided by 3, you get x equal 3. So you can do a check and see if that's correct. And so 3 times 3 is 9. 9 minus 4 is 5. So 6 to the 5th equal to 6 to the 5th. Yeah, that's correct. So in question 8 here, from, of course, this is from the homework 5.1. Similar thing. We're going to see, let's see, we did this a few times where if you have negative, you can switch to the form to negative exponent, or if you have it in negative exponent, you switch it to positive exponent. But you see the 4 and 16 not the same. 4 is not the same as 16. So we can ask, can we make the 16 a 4? Of course, yes. 16 is 4 square. So instead having this thing, we can say that 16 is 4 square, right? And this 4 square 16 has an exponent negative x. And we just looked at the properties. If you have two exponents, you can go ahead and say negative 2x because you're going to multiply the two exponents. Now that we have same, we can adopt the same idea of x minus x squared is equal to negative 2x. If we put all to one side, we can get 3x minus x squared equals 0. So x 3 minus x equals 0. So x equals 0 and x equals 3 when you solve these. So, and you can try that. Is this just like I did with the other example? You can check it. So for example, for 0, you can try for 0 minus 0 squared equal 1 over 16, 0. And that's 1 equal 1. That's good. And you can try as well for the 3 and see. So try for the 3 and see if that's correct. So okay. This last question here is get used to transformation. So I would please review transformations from algebra, and of course ask questions if you're not sure, because if you need to look at the original function that we talked about, the original function of ex and what happens to it. So for example, when you do this, it has this negative ex, which means it's going to switch it to be reflection to the y-axis reflection. Then you have these negative, which means x axis reflection. So this graph now is going to switch this way. So it's going to be something like passing through -1. Right, something like this. But you have 3, which is the vertical shift plus 3. So this graph is going to go up 3. Since now it's at -1, you're going to add 3 and it's going to end up at 2. right? So so that's one way to do it, or you can do a reflection to the x-axis first, or you can rewrite it this way. So I would probably do this one this way, negative e, negative x plus 3. So I would do this reflection first, and do the other reflection to the y-axis and add 3. Whichever way you want to do, but start with reflection first before this vertical shift. And you can do similar thing to this one. Of course, you're going to say now they're almost the same. They're doing the same thing, same reflections. They're coming up almost the same here. So how do I distinguish? Of course, we did the intercepts. You see, now this one, this y-intercept is going to be the same for both of them because they both got reflected. They got pushed up by 3, so they land at 2. But these are not going to be the same because that's the x-intercept. So what is the x-intercept for this one? We know x-intercept is y equals 0. So 0 equal negative x plus 3. And so let's say bring it to this side. So now you're going to solve another type of this exponential equation. I did two kinds, and also when I summarize, I'll talk about them again. So this one, x-intercept, y equals 0. So plus 3, which means equal 3. All right. If you have, you see not same bases here, and you can't make the same. Now, if the this question I asked, can we make 16 a 4? The answer was yes. Here the question, can we make a 3e or this like that? No. So same question for e and 3, right? The answer is no. If that's not, if the answer is no, that means you need to take the log to both sides. And in this case, natural log is better. So you can take the log, common log, or natural log. So let's do it on this side here. So you have e equal 3. We cannot do that. We cannot make e 3 something or 3e something. So we'll take in this case, natural log to both sides. So, and you get, what happens is these two cancel each other because they're inverse of each other. So you get negative x equal ln 3. And you've done this in algebra. You divide by 1, you get this. So that's the x-intercept for this one. The x-intercept for this one is going to be let's see, negative 0. It's here. Then we do the same. Then that's gonna give us, this will cancel, negative 0.5x equal ln 3. Then you're gonna divide by this, and you get ln 3, negative 0.5. So now you can do an approximation using a calculator. So you do 3 natural log you get about negative 1.1, and this one, these x-intercept for this one, you do 3 natural log divided by 0.5, you get about 2.2. All right. So for this one, we get about 2.2. So that's the red graph. And for this one, we get about that. All right, there, almost one, about negative 1.1. That's it. So if you review the sketching, that will help solving these rational equations. That's also going to help solving not rational, exponential equations. And I did the two types. Type 1 is this, where they have them the same, and you move with the powers there. The type 2 is when you answer this yes, it's this type of question where you make them the same and you turn it into type 1. And type 3 is this kind, where you don't turn it and you just take the log to both sides. All right, thank you.